To visualize how an infinite series behaves, we use partial sums. A partial sum, S sub n, is the sum of the first n terms of our series. Consider a series where each term adds a specific value. We calculate S sub 1 as just the first term, S sub 2 as the sum of the first and second, and so on. Our framework for convergence is simple. If the sequence of partial sums approaches a single finite number as n goes to infinity, the series converges. If it grows without bound or oscillates, the series diverges. The divergence test is the gatekeeper of series analysis. It is your first stop when determining if a series has any chance of converging to a finite total. The rule is simple. If the nth term of a sequence does not approach zero as n goes to infinity, the series must diverge. If the terms don't vanish, you keep adding values that aren't getting smaller, making a finite sum impossible. Visualize the terms as blocks being stacked. If the height of these blocks does not approach zero, the stack grows infinitely high. You are essentially adding a non-zero amount forever. Remember, this test only identifies divergence. If the limit is zero, the test provides no information, and you must move on to other, more powerful tests. The divergence test is a powerful gatekeeper, but it has a critical limitation. It only proves divergence. If the limit of the terms is not zero, the series must diverge. The trap occurs when the limit of the terms is zero. In this case, the test is inconclusive. The series might still diverge or it might converge. You must pivot to other tests. Consider the harmonic series. The limit of its terms is zero, which satisfies the condition for convergence tests. However, the harmonic series itself diverges to infinity. This proves why we cannot conclude convergence just because the limit is zero. Consider the series of 1 over n cubed. To begin our analysis, we apply the divergence test. We examine the limit as n approaches infinity of the nth term, 1 over n cubed. As n grows without bound, the value of the fraction approaches zero. Because the limit is zero, the divergence test fails to give us an answer. It is inconclusive. Since the test is inconclusive, we must transition to a more powerful tool, the integral test. The integral test serves as a vital bridge between discrete infinite series and the continuous world of calculus. By representing the terms of a series as a function, we can determine the behavior of a sum by examining the area under a curve. Consider a sequence defined by a function f of n. The sum of this series and the improper integral of the corresponding function from 1 to infinity are linked. If the area under the curve is finite, the sum is finite. This symmetry means that whenever we struggle to compute an infinite sum directly, we can use the power of integration to confirm whether it converges or diverges. Before applying the integral test, you must verify three critical conditions for the function f of x. The function must be positive, continuous, and decreasing on the interval from 1 to infinity. Failing to verify even one of these conditions can lead to incorrect conclusions about whether a series converges or diverges. Always check these criteria first. Verification is not optional. It is the mathematical foundation required to bridge the gap between discrete series summation and continuous integration. The integral test relates discrete summations to the area under a continuous curve. Visualize the series as a sequence of rectangles. Each rectangle has a width of 1 and a height equal to the term a sub n. The sum of the areas of these rectangles equals the sum of the series. Because the rectangles lie under the curve for a decreasing function, the total area of the rectangles is bounded by the integral. If the integral of the function converges to a finite value, the infinite sum of these discrete rectangles must also be finite. This bridge links calculus to series. We are evaluating the convergence of the infinite series of 1 over n cubed. For the integral test, the corresponding function f of x equals 1 over x cubed must be positive, continuous, and decreasing for x greater than or equal to 1. We now set up the improper integral from 1 to infinity of x to the power of negative 3. Evaluating the integral as a limit, we find the antiderivative is negative 1/2 x to the power of negative 2. Applying the bounds results in a finite value of 1/2. Because the improper integral converges to a finite value, the infinite series must also converge by the integral test. The harmonic series, defined as the sum of reciprocals from 1 to infinity, is famously deceptive. We observe that as n grows, the individual terms approach zero. Despite the terms shrinking to zero, the series fails to converge. We use the integral test, comparing the sum to the area under the curve of 1 divided by x. Since the natural log function grows without bound as its argument increases, the accumulation of these terms also grows without bound. Therefore, the harmonic series diverges. The p-series test is the ultimate shortcut in series analysis. It applies specifically to series of the form summation of 1 over n to the power of p. Instead of calculating a complex integral every time, we simply inspect the exponent p. If p is strictly greater than 1, the series converges. If p is less than or equal to 1, the series diverges. Consider the harmonic series where p equals 1, which diverges. Contrast this with a p-series where p equals 3, which quickly converges because the terms shrink fast enough. The p-series is a cornerstone of efficiency in Calculus 2. It allows us to determine convergence by looking at the exponent p. Think of p as the speed at which terms approach 0. If p is greater than 1, the terms vanish quickly enough to keep the total sum finite. If p is less than or equal to 1, the terms don't decay fast enough. When p is larger than 1, like n squared, the series converges rapidly. Mastering this test saves significant time on exams. A common mistake in calculus is the converse fallacy. Students often assume that if the terms of a series approach 0, the infinite sum must converge. This logic is fundamentally flawed. Consider the harmonic series. As n grows, the terms 1n clearly approach 0. It is easy to be fooled into thinking this means the series has a finite sum. The condition that the limit equals 0 is necessary for convergence, but it is not sufficient. The harmonic series is the classic proof. Its terms shrink to 0, yet the sum itself grows without bound, meaning it diverges. When using the integral test, you must confirm 3 critical conditions. The most common pitfall for students is failing to verify that the function is strictly decreasing. If a function fluctuates, the integral comparison is invalid. Here, the function values increase and decrease, meaning the area under the curve no longer corresponds to our series sum. To avoid these verification errors, always use derivatives. If you can show that the derivative is negative across the interval, you have mathematically proven the function is decreasing and can safely apply the test. Consider the infinite series of the rational function 4n plus 1 divided by 2n. Our first step is always the divergence test. We check if the limit of the terms approaches 0. By dividing each term in the numerator by 2n, we see the limit simplifies to 4 divided by 2, which equals 2. Because the limit is 2 and not 0, the series fails the divergence test immediately. Therefore, we conclude that the series diverges. Consider the series of 1 over n to the 4th power. Our goal is to determine if this series converges or diverges. We recognize this as a p-series, defined by the general form 1 over n raised to the power of p. By comparing our series to the general form, we identify that the value of p is 4. The p-series rule states that if p is greater than 1, the series must converge. Since 4 is greater than 1, we conclude immediately that this series converges. This avoids the need for complex integration entirely. When encountering constants within an infinite series, we can simplify our analysis by pulling the constant out of the summation. For example, in the series of 5 divided by n squared, the 5 is a constant multiplier. We can extract it as 5 times the summation of 1 over n squared. Because 1 over n squared is a p-series with p equal to 2, we know it converges. Multiplying a convergent sum by a finite constant does not change its convergence status. In summary, constants serve only to scale the total, but they never determine whether a series converges or diverges. To master series convergence, follow this strategic checklist before you begin solving. For the integral test, always verify the 3 conditions. The function must be positive, continuous, and decreasing. Follow this sequence to maximize your efficiency and avoid common errors in Calculus 2. Mastering these 3 tests provides the foundation for your journey through Calculus 2. By identifying the right tool for each series, you save time and ensure mathematical accuracy. Looking ahead, you will build upon these skills to tackle ratio and root tests, followed by the beauty of power series and Taylor polynomials. Keep practicing these steps until they become second nature. Remember, your mathematical intuition is your greatest asset in calculus.